Okay, thanks everyone. Thank you for inviting me. It's been a great conference. I only have 10 minutes, so I'm going to go through this fairly quickly. There's a QR code there that links to these, not only to these slides, also lots of resources about CK, ML, maths. We're also about to produce an Agentic Web3 course, so that'll be available there as well. So please have a look at that. All right, I'll skip this slide because you know all about agentic. We've just had some great talks about that. Yeah, so as we were just hearing, we have a problem with machine learning, with AI, because they're very difficult to really understand how they work and what they're doing, what that is based on. And we're tending to trust these things rather blindly. And it would be nice if we could have some reason behind that and have some confidence and some understanding of the risk involved. And the potential problems we get. I mean, if we're looking around DeFi, we could have huge problems if we are using AI to make decisions. It could lead to great financial problems, it lead to reputational problems. We've seen in training machine learning that you get potentially we get bias in the way that the training is done. And then there's the whole issue of compliance, whether they, if we're using agentic agents to do trading, are they following any type of compliance regulations? One of the problems when we get to try to work this out, though, is that we get a bit of an impasse. So blockchains and certainly and ZK as well, I'm going to come on to, they want to be deterministic. We want to have reproducible outcomes when we do some transaction. And we want the logic to be very clear and absolute. AI, machine learning, actually, I should say, really is probabilistic. It's working with statistics, with probabilities, and in fact with generative AI, large language models, and when we're using them to produce images, they do use randomness. They'll produce a different output each time you prompt them with the same input. And that is intentional. They're trying to be creative. So how do we, what can we do to help solve this? Well, one of my passions, zero knowledge proofs. These are a technique. They've been around for a long time, but they've proved very successful in the last sort of 10 years or so. They've helped with scalability on blockchain. They're a cryptographic method that allows us to prove some statement, and we use it particularly to prove that maybe some computation was done correctly. ZK rollups are proving that transactions were processed correctly. And an additional thing that you can get, the zero knowledge aspect, means you can have private inputs to those calculations. So you can prove something was done correctly without knowing all of the inputs, which can be very useful. So ZK is good at proving computation. Machine learning is just computation. So we could just put the two together, problem solved, we can all go home. It's a little bit more difficult than that. The motivation is clear, though. We would like to be able to say things like this, that we used a particular machine learning model, we provided some inputs, maybe private inputs, and that produced this output, and that was all done correctly. So that's what we're trying to aim for. That's what we want our proof to show. And it would be, a real paradigm shift if we could actually get that. And particularly with things like agentic Web3, we would like to be able to show that this decision to do this trade, we can prove that it was based on this particular information. So how do we do that? Well, you take your AI model and you turn that into a thing called a circuit that we can then use to create a proof. And I'm missing out a lot of detail there. Once we have that thing set up, then we can use that to create a zero-knowledge proof. This is just really a piece of data. This is just some numbers. And this is going to be quite small, of the order of maybe a kilobyte or so, that kind of thing. We can then pass that to be verified. We will have some special verifier, maybe a smart contract, that will be able to take that proof and verify that that proof is correct. What that proof could show is that some calculation was done correctly or some computation was done correctly. So that's what we're aiming for. Actually, before I go into that, I'll tell you the problems. So the first part, turning this AI model into a circuit. This is extremely difficult. And the basic problem with it is that zero-knowledge proofs rely on a certain type of maths. They rely on a very restricted type of maths. They don't use any numbers. They use integers. They use things called finite fields. These are sets of integers. There's a maximum value. And that's the assumptions we work with when we're doing zero-knowledge proofs. Machine learning, we don't have those restrictions. We use floating point numbers. They can be as large as you like. We do lots of complex calculations. And the two areas just don't go together. And this is a major problem, trying to create a zero-knowledge proof of a machine learning model inference. Okay. But what could we do with this? Well, there's some use cases here. This first one about credit scoring. This is useful because we could use this for privacy. We could get this to create a proof that shows that we meet some criteria without giving away our private information. Fairly standard type of use case. You can get them more complex. We could get them to be working with DEXs, AMMs, etc. Maybe you want to show that the way that this AMM has changed over time was done correctly. We weren't cheating our users. So all of this could use ZK. And here are some examples of projects that are actually trying to do this. So Ezekiel here, that's a library that is used to help develop zero-knowledge proofs of machine learning models. ZKML is confusingly called, it's another library as well. ZKTLS is a similar thing, not for machine learning particularly, but it allows us to do oracles. It allows us to show that a particular data source is correct, and also to do selective disclosure about the data that comes from a data source. So all really good stuff. Okay, so what the problems, as I say, the ZK and ML just don't go together very well because of the underlying maths. And this means that it's very expensive. There's lots of computation involved in creating a proof. So imagine I'm talking to a large language model. I put in a prompt, something simple. It gives me an output. It'll do that in a few seconds. If I want to create a proof of that, that is incredibly difficult. A lot of computation needs to be done to create a zero-knowledge proof. Now, about 18 months ago, one was completed. They managed to do this on a previous version of ChatGPT 2. But this is a version that had 1 billion parameters, and it was seen as something of a threshold that was passed. But just to generate that proof, just to show that going from that prompt to the output was correct, took 90 hours of computation to do that. So not really feasible. But things have got better. So we've managed to get that down. We're managing to tweak the way that we create these proofs and set up these systems. And we're getting all of that down. So you can now do it in the order of minutes, quite a few minutes, sort of under an hour. There are specialized ways of creating the ZKML systems to do that. But it's still problematic. And certainly for the types of use cases we would want, it's still not really there. We want to be able to send in a prompt, get an output, and get a proof back at this, within a second or so. So we're still not quite there. Also, the expertise involved. These are two very complex areas. There are not many people in the world that understand all the cryptography around ZK, and similarly, there are not many people who understand all the complexity around machine learning. So to get people who understand both is quite difficult. But it's, I think, certainly worthwhile, and we are getting quite a number of projects. So we've got projects, for example, Modulus Labs, Ezekiel, I've also already mentioned, and we're getting specialized hardware now. So people are building special hardware, special circuits that are ZK friendly, that they will be able to do these computations very quickly, and these help to speed up the whole thing. Okay. But the vision is that we could have our agentic economy. We have agents that are doing trades based on some machine learning models, and then we could have zero-knowledge proofs to prove that those particular models were used and that they ran correctly. So we have a problem with trust at the moment, and ZKML can help with this, but at the moment we do have problems with performance. There are problems getting these two things together. The deterministic aspect, for example, is very difficult for ZK. It doesn't handle randomness well. But it's something that we are making progress with, and I think is worthwhile. Yeah, and that's it. So I went through that rather quickly, but I'm happy to answer questions about that. Thank you.
Just so curious. Is it on? Right. I guess this unknowing, like basically you can achieve something, but you're gentle. Like the million things you don't see, but you know you did it correctly. That's kind of like, can you give us some fun business use cases in the future, basically? Because I'm thinking about like databases where you can't steal credentials because you don't see like a million credentials. Because you know you can. That's I'm thinking. That's maybe one example that you can just do one thing, but you can't just break in a database and like steal like millions of financial data.
Yeah, so yeah, it has. Well, ZK generally has good use cases around identity and doing selective disclosure of identity. So you could prove some aspect of your identity and create a proof that people will accept without giving away everything. People have used this with. There's a project called ZK Passport, which can take details from your passport, create a proof of that, and then you don't need to give them your whole passport. You can just say, you know, I do have a passport. It's been, you know, it's in date. It was issued by a valid government. That's all you need to know.
Amazing. Okay, we have time for one question, and then we're going to go to a short panel. Any question? All right. Okay, there's one question there. So.
I'm not the expert in this area, so just clarification of like with the verification step, right? So given I have a proof that your passport has not expired or doesn't expire until said date, right? How do I then take that proof? And like, what are the steps I take to actually verify that this is the case? How do I go from the proof to the knowledge?
Yeah, good question. Thank you. So before you do all this, there's some setup involved. So you do a setup of the system. So you set up something that will do the verification. You set up a kind of an algorithm for that is available. You set up the thing that is going to create the proofs. And so those things those two people or those systems need to be talking to each other and come to agreement about what verification means. Once you've done that, then you can create proofs based on an individual passport, for example. That proof will then go to the verifier algorithm, which will then say yes or no. And the important thing, the zero knowledge aspect, is that verifier just gives out one piece of information. It just says, yes, this is a valid proof, or no, it's invalid. And it doesn't learn anything else.
Sorry, just a very quick follow-up question. Sure. Does that verifier then require the private information or not?
No. So what the verifier gets is the proof, plus you may give it some public information. You don't have to, but the private information is kind of in the proof, but it can't be reverse engineered. So yeah, it doesn't learn anything about the private information.
All right. We thank you so much for your talk.
Thank you.